Welcome. So what I wanted to do with this final bonus lecture is not introduce new material that you're going to use on the quiz or the assignment, but give you a little bit of a glimpse into the power that you have now at your hands with propositional encoding. So for your course projects, you have a wide range of topics and a wide range of use cases, and a lot of you in the class have already figured out that you can solve some really interesting problems as long as you model the problem correctly. You write down the constraints declaratively, you turn the crank as that solver gives you interesting results. But this can really be pushed to the limit. And what I want to do is sort of describe how one aspect of the course is actually something that I used for another aspect of the course in an advanced way to try and get the job done. Now, some of you have been contributing to the contests throughout the course. There was 3 of them. 2 of them were to come up with very complicated natural deduction proofs. And the final one, the thorny theories one, this was stuck halfway in the middle of the course, and it's to come up with the most complicated Boolean function, so your truth table that maps to zeros and ones, and complicated in terms of the size of the formula that's required to represent it. So anybody can submit a formula over 3 or 4 or 5 propositions, and the more complicated that formula is, the more connectors, ands, ors you use, and the more negations you use, the higher its score is. But anybody can go and challenge something that's on the leaderboard to say, I've come up with a different formula that has the exact same semantic meaning, so the exact same true, false satisfaction for those sets of variables. And if you come up with something smaller, then it sort of takes people down that leaderboard ranking. And so what you find if you go to the leaderboard now, a lot of the entries are either colored green or red. And if it's green, it means that it's the optimal formula. You're not going to find something that's any smaller. If it's red, it means that there's something that's better out there. Now, there's been some discussion just starting now on techniques on how you would turn something to a little bit more efficient. One trick that a lot of students are using is that if you have the negation of a particular variable, and I'm going to use the Python syntax because this is what you'll see on the online, the website, and you have the negation of something else, if this is your submission, then this is equivalent to saying that it's the negation of x and y. Right? These 2 things are equivalent, and it's just De Morgan's that's been applied here. And if you count it, you have 1 negation, 1 disjunction, and 1 negation here. Here you just have 1 negation and 1 conjunction. And so the score of this is equal to 3, and the score of this is equal to 2. And this is how a lot of the challenges have been happening, just sort of syntactic changes to reduce the score a little bit and sort of drop down that formula. Another approach that people use is to write out the truth table. They have either 3, 4, or 5 propositions. So 2 to the 3 is 8 possible rows inside of there. And then try to come up with a formula that sort of tackles that specifically. And this has been successful in a number of these cases where a really large formula was submitted and a really small formula was found that was even better. But this doesn't answer the question. How am I coloring these things red and green? Do I have some special trick and technique or some sort of secret eye to figure out, what works and what doesn't to find the smallest? And how do I know for sure that the optimal is the optimal and you can't find anything smaller? I'm not spending my evenings and weekends cranking through all of the possible formulas that could be written on 3 variables. Instead, what I've done is at the start of the course, I've written a model, a propositional model, that solves the problem for me. And so what I'm going to do in this bonus lecture is describe a little bit of what that propositional model looks like, how I encoded the problem of finding encodings into propositional logic itself. Okay? So let's dive in. If we're going to take a look at this, let's use a base case example. Let's say we want to reduce this formula here where we have, and I'm going to use the regular signs for this to describe the different gates and describe the different propositions and formula that we have. If we have the negation of x and not y, right? If we were to look at the tree that makes this up, right? So let's write this down. We have negation. Comes down to a conjunction. Actually, I'm going to write the trees on the side. We have the negation at the top, a conjunction underneath an X and a negation and a Y, right? And if you look at this and we were to push the negation in using De Morgan's, it's the same thing as saying not X or Y, right? The double negation happens here, and I'll write this a little bit bigger. We've moved from something which has a score of 3 to something which has a score of 2. Again, we're just counting the negations and the disjunctions or conjunctions that exist inside of here. And if we want to see what this one looks like, there's an OR on the outside, there is a negation here, there's an X, and then there's a Y. Right? And so these are the two sort of parse trees for these formula. And now what I want to do is devise a propositional theory that, given this original one, is going to find a circuit or find a formula. I'll connect those two things in just a moment, to find a formula that's of smaller size. Now, the first thing that I need to do, and a lot of the projects sort of follow this same sort of pattern, is you need to restrict what size do I care to look for. So I need to choose the number 2 and look for a solution, choose the number 3 and look for a solution. If somebody submits a formula of size 20, what I've been doing is say, let's try and find an equivalent formula of size 5. If that fails, try it of 6, of 7, of 8, of 9, all the way up until I find the first number where it works. And that first number where it works, I know that that's the smallest formula that you could possibly find. There may be many versions at that size, but at least that's the smallest size. Okay. Now, I've mentioned gates and circuits a little bit, and you might find this in some of the other courses in computing. When you start to deal with actual circuits, what you're doing is you're combining these logical operations on actual physical hardware, right? And so an AND or a conjunction is the same symbol that you might see in a course like this that says you have an AND that takes 2 inputs. Maybe this is an X and this is a not Y, and it has a single output that describes, the conjunction between these two. Disjunction over here where you have a not X and you have a Y, and the symbol you might recognize is this one here, right? And so this is the disjunction between 2 different inputs. This is what I mean by gates and circuits. What we want to do, and essentially a formula is just a circuit that's in a tree-like structure, and we want to be able to compute this circuit and figure out what gates are required. Okay? So let me erase this again and start to talk about what some of these propositions actually are. Now, if I wanted to find a formula that has exactly 2 gates, right? So 2 possible things that I could do to propositions as inputs and give as an output, then what I will need is variables that say G1 is the output of gate 1, G2 is the output of gate 2. And now we need additional propositions that say things like G1 is a negation gate. That's a little bit small, so let me redraw it. I have propositions that say G1 is a negation gate, G2 is a disjunction gate, or G1 and G2, right? I'll do these all for G1. G1 is a conjunction gate, right? So if this proposition is true, it means whatever gate G1 is, its output is going to be true. If this holds, it means that gate 1 is a negation gate. If this holds, it means that gate 1 is a disjunction gate, and this means it's a conjunction gate. And so if we look at the solution that's going to come for this particular formula, we're going to have that. Let's actually put it up here. This could be our G1, this could be our G2, right? It's a bit small, but G1 is the top one, G2 is the smaller one. We're going to have that G1 is a disjunction gate, and we're going to have that G2 is a negation gate, right? And what we're going to be doing is asking the SAT solver to figure that out for us, right? Find an assignment to these gate variables that choose the type of gate it is, choose the connections between the gates, and make sure that all of the logic sort of holds out in the end. All right, so let's dive a little bit deeper with this. We have propositions that say what is the output of a gate. We have propositions that say what is the type of a gate. We need propositions that say two individual gates, gate I and gate J, are connected, and we need propositions that say there is an order between I and J as well. Now these are very closely related. The connected proposition, this just says that there is a direct connection between I and J. The output of I is connected to an input of J. The order just means there is a sequence of connections that allow you to go from I to J. And we need that sequence because what we want when we generate our circuit is for it to be a tree and not to have any cycles and not to have any sort of loops that bring you back together. In real circuits, you could have directed acyclic graphs where you could have things that come back together. But in the formulas that we're computing here and what we're asking you for the Thorny Theories contest is that it is a tree that you create. So it is a formula and it's a parse tree that you create from it, right? So to make sure that it's a tree and we don't have any of these cycles, we need this second type of proposition. Okay, so the first set of constraints that I'm going to describe gets at this property of it being a tree, right? And so if we wanted to say that if two things are connected, it means there's an ordering between it, then we have a constraint that says if I is connected to J, it implies that there is an order between I and J, right? So this is how you seed the orderings that are going to be in your theory. Another thing that we have here is that if you have from I to J, a particular ordering, and you have an ordering from J to K, then this means that there is a way to go from I to K. All right. Now, visually, what's happening here is we have some gates I, and we have some gate J, and we have some gate K, and we say that there's an order between I and J. We say that there's an order between J and K. This means that there has to be an order constraint between I and K as well. So this gets us the transitive closure of all of the gates that we're building inside of our formula, inside of our circuit here, okay? And this is the second constraint that we require for this type of ordering. Now the final one is to say for every possible gate, it's not the case, or the final one to forbid cycles inside of our formula here, it's not the case that you've ordered I before I, right? So, when we're saying that we have an order proposition for every I and every J, all of our possible gates, we need to say that you're not allowed to order I before itself. So if you combine this fact that you can't have a, order before yourself along with the transitive closure here that says, if I goes to J and J goes to K, then I goes to K as well. These things combined allow you to say that there's no cycles inside of the graph that we've built. So this rules out the cycles, but it doesn't rule out the idea of having directed acyclic graphs. You could still have something that looks like this here, right? Which we don't necessarily want, right? So like if this is a negation, this is a negation, and this is like a disjunction or something like that. We don't want to build up our graphs like this because it's not easily represented as a parse tree and it's not what we're looking for in terms of the submission. So how do we rule out directed acyclic graphs? Well, one way that you could go about doing this is to say that, make sure I get this constraint right. You can't have it that connection I, J, or connection I, K. Right? So what we're saying here is that for every I, it can't be connected to two different things. Now, we need to sort of take the dual notion of what's happening with this flip. If we look up here, this gate 2 is connected to the input of this gate 1. I'm going to put arrows on this parse tree. We don't normally use arrows, but this is the way that the connections are flowing. And so what this says is, if you have any node inside of your parse tree, you can't have two different edges going up from that node, right? You can only have one parent inside of what's going on here. So this is essentially saying you only have one parent inside of the circuit that we're creating. So for every individual eye, it can only be connected to a single input of another gate. So every gate, its output goes to exactly one other place, and that's it. Okay? At most one other place. And so this is something that means that it's going to get us our tree structure. When you combine this constraint, this type of constraint, with these here that make sure that we don't have any cycles inside of our graph. Okay, so now we're getting closer to building at least a tree, but we haven't connected anything about the logic yet. There's nothing about the input formula, and there's nothing about making sure that the output of our final circuit is matching what it is that we hope for. Other constraints that we need is that every gate has at least one input, right? And so we have a big disjunction over all of the possible inputs that we can have. Now these are going to include, in our example here, gate 1, gate 2, but also our input variables x and y, right? Because these are going to be inputs to the entire formula, and the output of it is going to be a true or false. So you can imagine this parse tree being our circuit sort of flipped on its end. The inputs are the x and y, and it propagates up, and the output is the entire formula, whether or not it's true or false. So for all of these, we have a big disjunction that says there's some connection to ik, right? And so this is, I'm going to use universal notation just to describe, it might be a bit confusing because we have predicate logic. This isn't predicate logic. We want to say for every k inside of our gates here are just G1 and G2. So for every k inside of our gates, we have a disjunction about all of the things that could be connected to it. So we want to say for every single gate, there's at least one input coming in, right? And if there's at least one input coming in, it means that every gate is being used in some way. We don't want any extra gates just sitting off on the side. And so this is a constraint that makes sure that we have an input for every single gate. Now, if we want to restrict what the individual gates look like based on their type, then we have information based on the type of gate here. So if a gate is a negation gate, it should only have one input. If a gate is a disjunction or a conjunction gate, it should have at most two inputs. And so the way to get at those constraints are as follows. So if we say, again for every possible k in the gates, if the gate is a negation gate, if we've decided that it should be a negation gate, then it should be the case that for every possible set of things that could go into it, so I, k, and this is here, negation, connected, j, k. Right, so what this is saying is, if we decided, if the SAT solver chose for gate k to be a negation gate, then it means that for every pair of ij, other things that could be possible inputs inside of here, at least one of them is false. And if you say at least one of them is false for every single pair, it means at most one is going to be true. And so this is how we say that negations have at most one input. Right? Now, if up here we're saying that every single gate has at least one input, and we say that negations have at most one input, these two things combined tell us that negation gates have exactly one input. Right? So this is how the constraints sort of combine up for these things. Now, the other one is to say that there's at max two inputs, no matter what it is. Of course, there's going to be at max one input for negations, but for any any gate, no matter what, there's going to be at max 2. And so what we end up doing here is saying that for every trio of gates, yeah, so it's basically for every H, K, I, and J, we have it's not connected H, K, or it's not connected I, K, or it's not connected J, K. And so this is saying at most 2 inputs. Right? And so here we're saying, you know, for a given gate K, one of these 3 things must be false. We're looking at every trio of possible inputs to a gate. One of them must be false. This is a way to say that there can be at most 2 inputs that are connected to it. And so this is restricting the inputs to a gate to make sure that we only have at most 2 and we have at least 1. And so you might find that there's a disjunction with only 1 input. But because we're doing this in an incremental fashion, it's going to use it as most efficient as it possibly can. So it will use the full 2, but it won't use any more. Okay? Because we don't want a disjunction to have 3 inputs to it. In circuit design, you absolutely can do that. You could have you know, a disjunctive thing with multiple inputs that come like this. But the way that the Thorny theories are scored is that every conjunction or disjunction needs to have exactly 2 sides, and it counts as 1 inside of the score for that particular formula. And so for this reason, we want to say there's at most 2 possible inputs. Okay, so let's take a step back and see where we are. We have propositions that define the outputs of the gates. We have propositions that define what is the type of gate that's going to be there. Propositions to define how we connect the gates to one another. And propositions that say whether or not a gate is ordered before another. And this one is just an auxiliary type of proposition that allows us to say things like there are no cycles inside of what we're building, and to say things like it's a tree in what it is that we're building here, right? So we're going to be building this circuit in a tree form. And then we have these constraints here which tell us, you know, what are gate connections allowed to look like. Negation gates have exactly 1 on the input, and disjunction or conjunction gates have at most 2 on the input side of things. And so this is sort of the preliminary stuff to sort of set up the theory and what a valid looking circuit looks like. And again, we still haven't tied anything from this theory to this theory. We just know that they have the same inputs. X and Y are inputs for both of them. Okay? And so now the next step would be to implement the actual gate logic. So I'm going to separate the space here and talk about the gate logic itself. If we wanted to say, what does it mean, given the inputs to a particular gate, what the output should look like, we need to follow the actual semantics of negation, disjunction, and conjunction. So I'll show just a couple of examples to sort of drive this point home. Put this here. If it's a negation, so let's say we have G2 is a negation gate. Then we want this if G2 is a negation gate and hold on one sec. Right. So what we need to do is in every possible way that things could be connected, you need to define what the input and the output is. And so what I'm going to do is give an example for a particular gate, G2, a particular way that we've set it, you know, its negation, and the possible inputs that could be there, just to give a sense of what these constraints look like. Okay? So if I start, if G2 is a negated gate, and what do we use up here? G2 in our end is going to be negated. Its input is going to be X. So if G2 is negated and we have X, then this should mean that the output of G2, right, which is just G2 without any sign, this means this is the actual output of that gate, then the output of this should be the negation, right? Because X is true. Right? So if X is true and G2 happens to be a negation gate, and we've connected X into G2 as that sort of connection for the circuit because of all of these constraints, then the output of G2 needs to be false. And because this is an if and only if, the reverse happens as well, right? If G2 is a negation gate and X happens to be false, then G2 has to be true, right? And if we look at what happens, again, up here, with gate G1, we're taking G2 as input and Y as input. And so we have something that looks like this. If gate 1 is a disjunction, and we have the fact that G2 holds or Y holds, then we have an if and only if for the output of G1, right? So under what conditions will G1 be true? It's going to be true exactly when you've decided to say G1 is a disjunction and G2 or GY hold, if this was the assignment that was happening. Now, the actual implementation of this and the actual constraints that go in are big disjunctions about this, right? So if we've decided that this is the case and this is here, then G1 has to go, but maybe we decided something else entirely. So, you know, it's what it sort of looks like is it's a single if and only if on this, and you would have things like maybe you decided G1 should have been a conjunction, and the inputs for G1 were X and Y, and if that was the case, then this is what would be defining G1 as an output. And so all of these different possibilities, a huge number of constraints, are being generated automatically for this theory to sort of explore and define what it means for a single gate in a circuit to output the correct response. Here is an example where the correct response is for a disjunction. Here's an example for where it's a conjunction. Here, negation, disjunction, conjunction. This is what it kind of looks like, but we have these constraints repeated again and again and again for all of the different ways that you could be combining these things. And so this gets you maybe 80% of the way, right? And what we have so far is a way to define a correct circuit, but we don't have a way to say the circuit that we have as input should be the same as the circuit as output, right? So how do we connect the fact that I want the exact same answers to, you know, X and Y set to true and false goes to the same, you know, column in the truth table for the full circuit? How do we tie these two things together? And this is the final part and probably the most difficult part of this entire thing. If you've made it so far, congrats. This is by no means an easy encoding, and it took quite a bit to put together. So the final thing to note here is that we want to take a look at the truth table for this function. We want the truth table to be exactly the same. And so if we look at what's going on, we have X, Y, and we have our final formula. And yes, we've used a particular way to define this function, this Boolean function, using these connectors and stuff. But really, it's the function we care about, not the actual connectors in the original. And so if I write out my truth table, 0, 0, 1, 1, 0, 1, 0, 1, right, what do we have here? I believe it's 1, 1, 0, 1, 1, 1, 0, 1. So the only time it's false is when X is true and Y is false. Yeah, so this is the truth table that we're trying to capture. Now, once we've built this truth table, we can name each of these rows. Let's say that's A, B, C, D. And so we have a special label for each one of the possible assignments for our input variables X and Y. Right, so now we have A, B, C, D. We can throw away this entirely. The fact that, you know, it has a score of 3, I don't care about for my encoding, but I do care that for every one of these possible rows, A, B, C, D, that the circuit that I build is going to have the exact same result. And so the constraints that are sort of tying that together is it's connecting the models of the two. And so what we have here, I'll use 0, 0, this first one. So let's talk about what the constraint looks like for A. We would say that X for model A is false, and Y, these are unit constraints, so this has to hold no matter what. You can't choose any other value for these. Y for model A is false as well, and we need to pick one special gate of all of the gates that we have as our output gate. This corresponds to the very top of the tree. You can choose it arbitrarily, and then the SAT solver will figure out what's going on for you. So I'm going to choose one here to be my special output gate, right? Because it's at the top of the tree. And so the output of this gate for model A has to be true, because it's true inside of this truth table. Right? If we look at another one, C, this says that X for model C is true, and Y for model C is false, and the output of our special gate 1 here for model C is false as well. So these, technically they're constraints, but really they're saying these propositions, you have to set them this way. There's no other way that you can do it. There's no disjunctions here. There's negations, but they're right on the literals. And so when you give this to a SAT solver, it's going to say, okay, I've got all of these propositions, XC and YC and so on. I'm going to set XC to be true, YC to be false, and G1C to be false, because it's the only way to satisfy these things. And what has to happen now is that you don't just have this set of gates for, once represented inside of your theory. You multiply these set of gates once for every row of your truth table on the input Boolean function. And so we have here gate 1, comma A, we have gate 1, comma C, gate 1, comma B, gate 1, comma D, we have gate 2, comma A, B, C, D. So for every one of those possible gates that we're trying to construct a theory for, we need a cloned copy of each one of these to say, this is the output of that gate if this was the row of the truth table that we're currently trying to evaluate. And we are currently trying to evaluate is a SAT solver trying to find a solution to all of this big mess for us, right? So let's take a look at some of the constraints and see what implication that has. Because it's sort of going back to the drawing board here and saying, we don't just have these two propositions, we have each of these propositions multiplied by the number of rows in your truth table. So if we look at this, the connection between gates and the order between them, it has to be the same across all of your rows. So this constraint doesn't have to change, nor does this one, nor does this one. We're going to connect the gates, and we're going to use these propositions, not with a clone, because we don't want a different circuit or a different formula for every one of these rows of the truth table. We want the exact same one, so we do these only once. If we look here, the fact that it's a tree, we do it only once. If we look here to say the connection on the gates, everything has an input, we do it only once. If we look down here, it says gate K is a negation gate and implies these connections. We do it only once. So these decisions up here, gate I, gate J, should it be a negation or a disjunction or a conjunction? We only have to do that once because we want the circuit to be exactly the same no matter what what row of this truth table that we're dealing with. Okay, so all of these constraints that are on this side of the board, we only need to do once for the entire theory. And if you look at the constraints on this side of the board, especially these up here, which talked about what is the output of gate 2, it's not just the output of gate 2 in general, it's the output of gate 2 given a particular row. And so for every row in our truth table, we need to replicate and clone all of these constraints tied to that row. So how does this one change? The fact that gate 2 is a negation, that is done only once because it's the same circuit for everything. But if we're dealing with, say, A is the one that we're trying to write these constraints for, here we would say X is true in A. It means that G2 is false in A, right? And it would be if X was true in B, then G2, or if X was true in B, then G2 would be false in B, and so on. So you repeat every one of these constraints for every one of these rows, right? I did miss one particular constraint over here, and this is a common one that you guys all know in the class. You want to say that one of these things has to be true, so you can't have a single gate take on two different values. It needs to be exactly one value, right? This is just saying that you need to pick one of these things for an individual gate. And so, but this is on that side of the board. It's constraints that don't have to be replicated. These constraints do. They do need to be replicated once for each row. So what does this look like in the end? We've described what some of these variables and constraints look like for that particular setting. How big is this theory and how complicated is it to start solving these things? Let me pause for a quick moment and show what happens if we try to take this as input. We get our Boolean truth table from this and generate this as output here. So let me show quickly. This is the entire encoding. It's using the same libraries that you know and love for your project course, right? So we're pulling in the NNF library, ANDs, ORs, operators, and so on. The same tricks that I've been giving you. But the implementation of this is quite detailed in advance, right? The constraints are the similar as the ones that you've seen on the board. We talk about forbidding cycles. We want to make sure that we force it to be a tree. And so, you can have at most one parent as the type of constraints that go in. And everything that you saw on the boards in math is reflected here in the actual code. And so if I scroll all the way down to the bottom to how things are actually running, if we say that our theory is the negation of x and negation of y, and we want to improve on this, and we want to find one of size 2, once we run this, we find that configuration for this particular thing is that y or the negation of x. And so if we go back to it, if you use De Morgan's here, it's not x or y is what goes into it. And so that's what it's found in the end. It's found a circuit that works with just 2 gates inside of it. And so you can see here, these are the connections. It connects x to gate 1, it connects y to gate 0. The indices are different than what you saw on the board. And the connections between these individual variables and the outputs and so on. Now, this very, very small problem, after you create all of the constraints and the propositions and copy for the rows of the truth table and everything like that, it has a size of 635. So this is the individual connections inside of the full encoding that I've created. It has a height of 5, so it means it's pretty shallow, and I'm adding constraints that aren't too big and complicated, but many of them. It has 35 variables. That's just for this small problem with x and y as inputs. The number of variables required to find the optimal circuit is 35. And when you run this through the Zeitman encoding, it comes up with 215 variables, 180 of them are auxiliary, and 657 clauses. And this, of course, is fairly small, and the SAT solver is able to find something in, a fraction of a second, very, very quick. And so it's able to do things very quickly because of the engineering that goes into these SAT solvers. But again, this is a very, very small problem. So if I pull up the actual Thorny Theories contest site, this is where the leaderboard stands, right? So this one here for just 3 propositions, it's sitting at a size of 14. It's colored red, so it means it can be improved. And just to show that in action, that theory down here, let me comment this out. I don't want to print the solution for you so you can find it yourselves. But this is the theory. I copied directly from the submission that's on there. And I'm going to iterate through and try to find a circuit or a formula of size 1 all the way up to 14. In Python, this will be 1 minus the 15. And 14 is the submission, right? So that should be improved. And if we go like this to see, it iterates through and it says there's nothing for bound 4, 5, and so on. But it finds something for 6. And if it finds something for 6, it's going to find something for 7, and for 8, and for 9, and so on. And so what we're actually finding is the submission of score 14 for these 3 propositions can be improved down to size 6. And so if somebody comes and successfully challenges this, it can drop it from first place down to third, at least, right? And so anything that's red inside of here is fair game. And if it's red, it means I've been able to find an improvement on this theory using the encoding that we have. Okay, and if you're curious about the size, solutions for size 6 or 7, we're talking about thousands of variables created and tens of thousands of clauses that are sent to the SAT solver to be able to figure out this a solution to this circuit. And so what you can see is that even in this very, very small example, we only have 2 input variables, and we only have, a number of size 2 that we're trying to find on our circuit. You still have a large number of propositions that are created because of all of this cloning that has to happen, because of all of the connections that could be possible. And you have a huge number of constraints. And that's before you even throw this to a Zeitman encoding, and it generates even more constraints and even more variables for the SAT solver to try and solve. Despite all of that, The SAT solvers today are extremely powerful, and if the encoding is done right, it is able to solve quite a large number of things. And so when you go back to the Thorny Theories contest page and you look at what some of these rows are colored with, everywhere that's green, it means that we've fed this in and we've shown that the smallest possible circuit is the one that's submitted, and there's nothing better that you can do. If it's red, it means that the SAT solver has found something smaller that could be used for this, and so every row that's red, there's a smaller formula that's going to satisfy that exact same set of rows in your truth table. And if it's white, it means that that particular Boolean function and that input formula, or the input formula that drives that Boolean function, the SAT solver has timed out. I've given it maybe half an hour or an hour on a decent computer, and it hasn't been able to find a solution. So this isn't, a perfect approach to solving this, and there's improvements that can be made for it. And it's not exactly the full theory. There's a lot of sort of finicky quirks that need to go into how to make these constraints work just right. But hopefully, if you've made it this far inside of the, this bonus advanced part of the lecture, hopefully this gives you a sense of the power that can be had if you model things correctly inside of propositional logic. The mere task of trying to challenge somebody's theory submitted to a Thorny Theories contest can be encoded as a SAT problem or a sequence of SAT problems itself, and you can find the optimal circuits using the right encoding. And so the complexity of this is sort of graduate level encoding that you can do for satisfiability and for propositional logic. And this is the stuff that you might see to solve real problems like scheduling, like resource allocation, like some of the project ideas that you've come up with. The more complicated the constraints and the sort of setup is for the problem you're trying to solve, the more complicated all of these things start to work together. So hopefully it gives you a little bit of a sense of what's possible with this. And again, thank you for all of this, and it was a really fun contest, and it was really fun to see some of the submissions. And if you do go to the Thorny Theories and you see a red row, make sure you go and try to challenge it. I don't necessarily recommend you try to implement all of this using SAT theory. Focus on your projects instead. But hopefully this gives you at least an idea of how it was that I was able to go and show what was optimal and what wasn't in all of these contests. All right? We'll see you online. Cheers.